Hey everyone, E.T. here, and welcome back to WYSTEM. We are now on Mathematics Part 2 of 2 with Computer Science Professor Lars Kotthoff. If you did not see Part 1, we learned a lot about math and coding and a bunch of cool things about graphs and plotting, so we're really excited to kind of wrap up the Mathematics Week tonight. If you are just joining us, welcome to WYSTEM. WYSTEM is where we are celebrating computer science and a bunch of different STEM industries. So we've got science, technology, engineering, and mathematics. And this is actually the last content video, which is crazy. We kicked this off in early May and it's already done. And tomorrow we have a very special session. Tomorrow is our wrap party. And so we are going to, at 6 p.m. tomorrow, we're going to be kind of reviewing what we learned over the last 4 weeks. And then also we're going to be selecting one lucky Wyoming student to win a 3D printer for their school. And so how you win that is in the last 4 weeks, there's been 4 secret code words. So there was one during Science Week, there was one during Technology Week, there was one during Engineering Week, and then there was also one that's showing up this week. The code word for this week may have shown up Tuesday night, or it may happen tonight. So you have to watch and participate. And then I'll show you here at the end of this video of once we have all of the code words, where to go, submit that by 6 p.m. tomorrow, and then we'll do a random drawing, and hopefully you're the lucky one that gets one of these really cool 3D printers that you'll be able to use at your school. So keep an eye out for those code words, and I'll tell you how to win and where to go to do that. And so anyways, I think I'm going to go ahead and let's go ahead and start learning more about mathematics and all the cool things. So I'm going to go ahead and hand it over to our wonderful host, Lars, and we'll go from there. So Lars, you're up.
Thanks, E.T., and welcome back, everybody. So on Tuesday, we talked about coordinate systems and how they're kind of behind all of the other stuff that you heard about, science, technology, and engineering. Well, maybe not so much science, but we're getting into that today. But certainly mapping and maps and 3D printing. For example, we had a look at this guy here. Let me see if I have this the right way around. Yes, so this is a 3D printed map of Wyoming, combining both mapping and 3D printing. And we have seen how with coordinate systems, we can describe things on a map. I live here, I go to school there, 2 points on a map. I can describe these in a coordinate system and now make a map from that, but also things that can be 3D printed. So again, for example, for this thing here, there's a point there, and there's a point there, and these are somehow connected, and then there's a bunch more points. I can describe all of these using their coordinates. The really cool thing about coordinate systems is that once we have the data, whatever that may be, a map or a 3D printed model described in a coordinate system, we can start to do things to the coordinate system. For example, we can scale it. And that's how you can make maps easily in different scales. You don't have to re-enter all the information. This is where I live, this is where I go to school, this is where the supermarket is, these kinds of things. Every time you want to make a different scale map, you just scale your coordinate system. Same thing with rotation and moving things around. Instead of re-entering all the data, we're just transforming the coordinate system. Really cool, not a lot of work, very easy to modify all of these things. So let's have a look at other things we can do with coordinate systems today. In particular, we don't only have to enter spatial data. Like there's a point in space at this particular position, and that's what we could use coordinates for. Or there's a point here on the map, and that's what we use coordinates for. Because this is much, much more powerful. We can express all kinds of other things as coordinates, even things that you might not ordinarily think of. And with that, we can show things in very interesting ways, and then we can manipulate them in interesting ways again. Let's have a look at some of the things we can do with coordinate systems. E.T., cue the first video, please.
Both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population.
Okay, cool.
And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world?
They can hear us talking.
The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
That was pretty cool, wasn't it? Oh, and by the way, for those of you who didn't watch on Tuesday, I just want to mention that because I'm a computer scientist, everything I do has to have some technical difficulties. So us talking in the background during the video, that was entirely intentional. It wasn't an accident. I think that that's probably somewhere in my contract. So everything going exactly as planned. Now, we've seen a couple of other things we can do with coordinate systems. You can take all kinds of things and then plot them on axes, and you can see all kinds of cool stuff. Now, I wonder what exactly else we could do with this. Let me share my screen with you, and let's see what else we can do with this. Okay, so here I am in an online graphing tool, and I've loaded some data up here. Let's make a graph. Let's make a coordinate plot just like we've seen it before. We have something called date. Okay, that doesn't look very exciting so far. And we have something called cases. Now, this is the number of COVID-19 cases in Wyoming over time. So something very relevant. Let's have a look what we can get if we put this into a coordinate system like this. So we see that, well, it starts on kind of March 11th here with the first case, and then it goes on. There's still only one case 1 day later, and then it increases and increases and increases until we get to April 2nd. I haven't shown you everything here. I will get into why in a second, but only up until April 2nd. Okay, so that's great, and that shows us how many cases we have over time, I guess. I wonder what else we can do with this. Well, let's do some mathematical modeling. Sounds complicated, not really. All we're going to do is fit a line through this. In the same way that if you draw this on a piece of paper, if you draw these points on a piece of paper, you might then draw a line through them. Let's have a look what that looks like. There we go. Ooh, that's a terrible line. That doesn't really look like what the points are at all. But before we have a look at how we can make this better, let me explain why we might want to do this. This line here is now a mathematical model of the points of all the data that we have plotted. And this allows us to do all kinds of things that we can't do without this mathematical model. For example, we can say what happens after the end of the data, in the middle of April, or in May, where we are now, or in June, in the future. We can use this mathematical model to forecast what's going to happen in the future. And this works pretty much exactly the same way that, again, you would do this on paper. You draw your dots, and then you connect them with a line. You can extrapolate this line into the future, and based on that, you can see what's going to happen there. So a very useful tool, in particular in a pandemic like we're in right now, because it allows us to see what's going to happen in the future and then do something or not do something based on that. So here, what I've shown you is just a simple line, what's called a linear model. And as you can see, that doesn't really fit very well. It doesn't look like the line really corresponds to the points at all. So let's have a look at a different type of model. Here's a quadratic model. There we go. That's starting to look pretty good. And for a quadratic model, for every step we take on the x-axis, we take the quadratic number of that number of steps on the y-axis. So for example, if we have 1 on the x-axis, on the y-axis we have 1 times 1. That's also 1. Okay, that's not very exciting. But for 2, on the x-axis, on the y-axis, we have 2 times 2, 4. Or, for example, on the x-axis 10, we have 10 times 10, 100 on the y-axis. So something that gets bigger much, much faster than the simple line that we had to look at before. However, there's still parts that don't really fit with this. In particular, these guys here aren't really there, and then it kind of goes this way, and then it kind of goes the other way again. So let's see if we can make this even better. We have lots of different functions, lots of different mathematical ways of expressing what happens with these x and y coordinates. So let's choose another one and see what we can do with this. I'm going to choose the exponential function here. Run. And there you go. This is starting to look really, really good, right? We're really, really close to most of the points. A couple of points are a little bit away, but these are kind of wiggly and going all over the place anyway. So that's looking pretty good. Let's settle on this. Let's say that the best model for these data points that we have here is the exponential function. So what does that mean? As I said before, we do this kind of modeling because we eventually want to predict what's going to happen in the future. How many cases are there going to be in the middle of April, at the end of April, middle of May, and so on and so forth. And this exponential function that we have fit now allows us to do exactly that. We can extrapolate that into the future. And using this model, we can say, well, okay, given what I've got from these data points here, what's going to happen in June? Now, you might not be familiar with an exponential function, so let's have a look at what exactly that looks like. E.T., cue the second video, please.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of -3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1024/1000ths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times, would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then, starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
Okay, so that seems pretty useful if we want to get to the moon, but well, it's kind of cold there, I think, so I would rather stay here. And not really what we want for the coronavirus cases in Wyoming, right? So that looks really, really bad. Okay, let's go back to our mathematical model and see what we can do about this. There we go. Okay, so this is only the data until April 2nd. And the reason I chose this particular date is, if you remember, around March 15th, Governor Gordon recommended that all the schools be closed. And around March 19th, he actually closed down all the restaurants and various other public places to stop the spread, to slow the growth. Exactly what we want here, because we definitely don't want this exponential thing happening here. And except that this takes about 2 weeks to take effect, because there's this 2-week lag between somebody getting infected and then showing any symptoms, and then they might go and get tested and find out that, oh, okay, I have the coronavirus, but I didn't know it for 2 weeks because there was nothing that gave me an indication I had this. So let's have a look at all of the data for Wyoming and see what happened after April 2nd. Here's another graph, exactly the same thing, except here I have now the data up until May 26th, so the day before yesterday. And still the first couple of data points here, exactly the same as before. But as you can see, this looks quite a bit different to what we had before. So let's see what happens when we fit an analytical, mathematical model to this. And I'm going to start with what we had before. I'm going to choose an exponential function here and see how that fits. And okay, that doesn't really fit that well, but it also doesn't look like an exponential function at all anymore, right? This just looks like a line now. Okay, let's maybe go back and try the quadratic thing, see what that looks like. That is pretty much the same, right? So actually, maybe what we want here is just a line. Let's try that. There we go. Pretty much exactly the same again. So it looks like we really have brought this exponential growth, which was terrible, down to something linear, which is much, much better. We have flattened the curve. You've all done the right thing by staying home, not going to school, not going to restaurants. This is what we're having a look at here. So this allows us to now say not only that back in early April, it looked really, really terrible, and we have to do something about this, which we did. It also allows us to go back and have a look at this now and see that, yeah, this did actually work. All of the stuff that you had to do that maybe you didn't like because you weren't allowed to go out as much anymore, that did actually slow the spread of infections. And that really, really worked in practice. And we should probably continue doing this, or maybe not. It also shows you that these mathematical models can change over time. So back in early April, what we had a look at was an exponential curve, and that was the best thing to do at that particular time. Here, now in late May, we're looking at a line, something linear, something very different to the original mathematical model, and it looks like this is the best thing now. So mathematical modeling is a very, very powerful tool that can help us to make decisions and that can help us to understand data better. And of course, for this, you have to understand the math behind it, which you now do, at least to some extent. So to take us out, let's have somebody tell us about mathematical models specifically in the context of COVID-19 and how these change over time, as we have just seen for the case of Wyoming. E.T., cue the last video, please.
Visualization is right at the heart of my own work too.
28th for our most recent episodes on COVID-19. Check out the playlist in the description. The COVID-19 pandemic has been dominated by numbers, especially the numbers of new cases and mortalities every day. But what's just as important as those numbers is how they're changing. Predictions on how they'll change over time depend on epidemiological modeling, which aims to mathematically describe how diseases spread. And this is what leaders are using to figure out how drastic the effects of the pandemic could be and what measures we need to take. Unfortunately, these models aren't simple and they don't always give clear-cut answers, which has led to some confusion about how to interpret them. On top of that, even when a model does give a clear estimate, it often ends up being wrong weeks or months later because our response to the model can change the course we're on. So if you see a model that overestimated something, it doesn't necessarily mean we overreacted. It often means we did exactly the right thing. One study that got a lot of attention recently came out of Imperial College London in March, and it predicted that without drastic measures, there could be up to 500,000 fatalities in the UK. It had a huge impact and even shaped the UK's response to the pandemic. But a few days later, the lead author told the British Parliament that he now only expected 20,000 fatalities. Now, any number bigger than zero is bad news, and honestly, talking about fatalities at all these days can be really difficult since we're still right in the middle of this, and these are real people, so forgive us if we sound a bit clinical here. But as bad as 20,000 deaths is, that's 25 times less than 500,000. That made some people think the model was unreliable or wrong, but in reality, both numbers came out of the same model. It's just that the 500,000 figure was if things continued as they were, while the 20,000 figure factored in the effects of new protective measures, and the predictions reflected that. In fact, those circumstances and the predictions are still changing, because models are constantly being updated to reflect new information. So to quote the statistician George E.P. Box, all models are wrong, but some are useful, and that's because of how they're designed. The simplest epidemiological models have three groups of people: the susceptible, who haven't caught the disease at all, the infected, who have it, and the removed, who already had it and either recovered or didn't survive. For that last group, the model assumes that once someone has stopped being infected, they can't catch the virus again or give it to anyone else, although technically we don't know for sure that that's true for COVID-19. Together, these form what's called an SIR model. SIR models start with some number of people in each group based on real-world data and use computer models to step ahead in time. At each step, the computer simulates some number of susceptibles catching the disease from the infected. Meanwhile, some of the infected become removed if they've had the disease for long enough, either by recovering or by dying. As the number of people in each group changes, that tells you how many people catch the disease over time. These models can be really helpful for making predictions, but they also come with challenges. For instance, epidemiologists have to determine on average how many susceptible people can catch the disease from one infected person. This number you might have heard of, it's called R0. When the Imperial College did that first study that predicted 500,000 fatalities, researchers estimated that R0 was 2.4 based on data from cases in Wuhan, China. That's lower than the latest estimates though, and it's just one reason modeling is so hard. Models depend on inputs like this, and those numbers aren't perfectly known, even where scientists.
Okay, so that hopefully helped you understand why mathematical modeling is so important and why we should really think about this. And with that, we're going to wrap it up. We're not going to go into any more math here. We're not going to talk about any more numbers. Back to you, E.T., and are there any questions that I can answer?
Awesome, yeah. So, does anyone have any questions? Let's see if we have any questions. So, I guess maybe I have a question for you, Lars. What would you say? I'm trying to think of something here. What is your personal favorite thing about mathematics?
Well, that's a very good question. I think it's really that it allows you to do a lot of things that you couldn't do without mathematics. We've had a look at 3D printing, we've had a look at mapping, now we've had a look at mathematical modeling. None of these things would be possible without math. And there's not a whole lot of math. Like in some cases, this is drawing some dots on a piece of paper and then drawing a line through them and seeing how well that line fits. But it allows you to gain some more insight into what's happening and make predictions for the future, which especially during a pandemic can be really, really useful to see what we should be doing and what we should not be doing. And maybe we need to change what we're doing in some way. And then there's a lot more stuff behind the scenes, or the actual math behind it, that makes it really, really exciting for me, just because you can do so much stuff with it, and just because you can apply it to pretty much everything. All of the other things that we've talked about, science and technology and engineering, there's math behind it that's making all of this possible, and that's making all of that happen.
Awesome. So how much mathematics is involved in computer science, the field that you teach at the University of Wyoming?
There's not a whole lot of math, I would say. My students would probably disagree with that. But there's math behind all of this, because in order to be able to program a computer, you should at least have a basic understanding of what happens behind, and then you're going to need some math to describe what's happening there. So it's really kind of far more on the applied side. We're not really doing what the mathematicians are doing, which is kind of weird. And that's why I'm a computer scientist and not a mathematician. But math is really all over the place, and not just in computer science, in pretty much all other areas of engineering as well, and in most of the natural sciences, in physics, in biology, all of the kinds of things there, you're doing some math as well. You might also be doing some really cool experiments, especially in physics, but then you need math to figure out why what you saw was actually happening, so that you can then, again, build a model, using some kind of math. And this model you can then use to make predictions about the future, what will happen in different circumstances. For example, gravity, we know that if I push something off the table, it will fall down. And our mathematical model of gravity tells us that, yeah, okay, if I do this again, it will also fall down. But it also then tells us that if I do go to the moon, for example, by folding a sheet of paper many, many times, and I push something off a table there, it will actually fall slower, because gravity is not as strong on the moon. And we can compute exactly, using these mathematical models, how long it will take, given the height of the table and the object that we're throwing down, how long it will take before it will hit the ground, both here and on the moon. And I can do that without even going to the moon. How cool is that?
Cool. And last question, Lars. If you wanted to brush up on mathematics, do you have any online or free resources that people can continue to learn more about math and get better at math?
Well, there are a lot of resources out there. In particular, there's a lot of cool videos on YouTube, and I've tried to show you some of them, of course, as per my contract, technical difficulties, so therefore we weren't able to do that. But you might be able to go back and have a look at those later. We will also have links to all the videos down here in the description. There are lots and lots more. In particular, for the coordinate song that we did on Tuesday, there's more videos like that. Have a look at those. I think there's enough that you can watch them all day. Your parents are really going to like that.
Awesome. Yeah, I had to watch that video like 2 times on Tuesday, and I was like, my gosh, that coordinate song is like getting stuck in my head. So thank you so much, Lars, for hosting Mathematics Week here for WYSTEM. And that's the wrap, folks. So let me just kind of tell you what's next. We just opened up the online submission form. If you've been watching all of the videos over the last month, again, there were 4 secret code words. I'm going to go ahead and switch over to my screen, and all you have to do is, if you see the video here, we have a link, submit the secret code words. Click on it, and there'll be a simple form that you just got to pop in your email address, your first name, where in Wyoming you live, what school you attend, and then the 4 secret code words. And then you can come down here, hit that submit button. And then what's going to happen is, so this form is going to be live for just 24 hours. So I'm going to take it offline about 6 p.m. tomorrow. We're going to do a random shuffle of all of the submissions. I'm going to draw one lucky name, and that one person, that student, you're going to get a 3D printer for your school. So, and hopefully now you've learned a lot about 3D printing and math and all that kind of stuff. There's so many things that you can do with that. So go ahead and click on that link in the description. If you joined us halfway through WYSTEM, no worries. We have all the videos recorded here on our YouTube channel, so you can go back and watch them. And again, look for those 4 secret code words, 1 for each week for science, technology, engineering, and mathematics. And we can't wait to award a winner. So that is it for Mathematics Week, but we do hope that you will join us for one last time tomorrow at 6 p.m. for our wrap party. So at 6 p.m. we'll be live again here on YouTube, and we will kind of recap the science, technology, engineering, mathematics, and then we will draw a name for the lucky winner, and then we're going to send you a 3D printer. So hopefully you guys enjoyed mathematics. Again, thank you, Lars, so much for taking the time, and we will see you back here on YouTube, and we're going to draw that name tomorrow at 6 p.m. You're not going to want to miss it. So, all right, ET's over and out, and I'll see you tomorrow. Bye, everyone.